Hi guys, so this is Vicky again, and today what we're going to do is we are going to try to tackle some of these FRQ questions. So this is a 2014 free response, and this is question number 1. And the first question here, it says, for the chemical reaction that occurs when the precipitate forms, write a balanced net ionic equation for the reaction. So we know that we have a tablet made out of potassium iodide, and we also know that we have the solution, which happens to be lead nitrate. Okay, all right, so based on this, what we have to figure out is that we need to realize that this is a double replacement reaction, right? Do you see here? Potassium iodide, lead, and nitrate. So what we're going to do is we are going to switch partners, outside with the outside, inside with the inside, and we are going to switch partners. So first thing first, what I like to do is ionize them. Just write all the ions. Okay, and this is Pb2 plus, and then I have NO3 1 minus, right? And I know that the outside with the outside, inside with the inside are going to be switching partners. So now I have potassium nitrate and lead iodide. Swap them and drop them, and I get PbI2. Now, how do I know which one is going to be the precipitate? So if you guys remember from my previous videos, we have the solubility rule, and if you guys remember the Lena column, the first column of the periodic table, Lena, lithium, sodium column. Lena, super slutty. She never likes to be in a solid relationship. Hence, she will always be in a aqueous solution. So that makes PbI2 the solid, because remember PbI2 was rule number 2 with AP history, so PbI2 is a solid. That means the KNO3 are going to be spectator ions. So I'm actually just going to delete all of those, and I end up with I minus plus Pb2 plus, yielding PbI2 solid. Now I go back and I just balance the equation, and right here I end up with my net ionic equation. And that's it. Super easy, right? All right, let's continue and let's talk about number 2. It says, explain what the reaction is best represented by net ionic equation. That's just because we have a double replacement reaction. Double replacement reaction. I'm actually just going to do bullet points for the sake of time. And then we also have spectator ions that don't really partake in the chemical reaction itself, right? And therefore, we are more prone to just wanting to see what the main gist of the chemical reaction was. And we call that the net ionic equation. Cool. Let's continue with B. I'm actually going to change colors so that we can see. B, it says, explain the purpose of drying and weighing the filter paper with a precipitate 3 times. So the reason why we do that, it's because we want to make sure that the mass is constant, okay? So the first thing, weighing it multiple times, that is to see mass is constant. And that is to make sure that there is no more water left over and we have pure precipitate. Okay, no more water is left and pure precipitate is obtained. That's precipitate is obtained. Okay, easy peasy, easy peasy. All right, let's continue with the next one. C. In the filtrate solution, is potassium greater than, less than, or equal to NO3 minus? So basically what I'm going to do is I'm actually just going to be looking at my molarity, right? So I have 0.2 molarity of Pb NO3 2. So it just so happens that I have 1 Pb and 2 NO3 minuses to create PbNO3 2, right? And if I happen to have 0.2 of the whole thing, that means I'm going to have what? 0.4 of NO3s, and I am going to have 0.2 of Pb2 pluses. So which one am I going to have more of? I am going to have more NO3 minuses than I will Pb2 pluses. Okay, easy peasy? Okay, cool. Let's continue with D. D is calculate the number of moles in the precipitate, okay, that is produced in the experiment. So let's look. It says that I have 1.698, okay, and I am looking at this number. You can either look at any one of these numbers because these two numbers, they don't really necessarily change. But I like to go with the smaller number just because that just means that I've basically driven off all of the water as much as I could. So I have 1.698 grams of the precipitate, right, minus 1.462. So this is basically, I am getting rid of the filter paper weight. Okay, so I am going to subtract 1.462 grams, which is the filter paper, and I end up with just the pure mass of the precipitate itself. Okay, so based on this, now I can do just regular stoichiometry. So I have 0.236 grams of PbI2. Okay, and I want mass at the bottom and I want moles at the top. So for every 1 mole of PbI2, it's about 461 grams of PbI2. Okay, and then if I do the math, grams and grams cancels out, I end up with about 5.12 times 10 to the negative 4 moles of PbI2. Does that make sense? All right, cool. All right, let's continue with E. So E says, calculate the mass percent of I minus in the tablet. So right now I already have the moles of PbI2, right? And I know that I have 1 lead, okay, iodide, 1 lead iodide per 2 iodines, right? So I am going to do 5.12 times 10 to the negative 4 moles of PbI2, right? So for every 1 mole of lead iodide, I have 2 moles of iodine, right? And that is going to give me the moles of I minus. And that happens to be basically 2 times that number, so it's 1.02 times 10 to the negative 3. Okay, now that I have moles of iodine, okay, I can actually find its grams, right? So 1.02 times 10 to the negative 3 moles of I minus. And the reason why I want to find the grams, okay, it's because I want to find the percent mass, like how much of the total is it, right? And that ends up being about 0.130 grams of iodine in the whole tablet, okay? So what is the tablet's total mass? The tablet's total mass was what? Up here, right? The mass of the tablet was 0.425. So 0.425 is the total mass of the tablet over this mass right here. 0.130 grams of just iodine times 100, and I end up with the percentage, which is going to be about 30.6% of just iodine. And that's your answer for E. Okay, cool. Let's continue and let's look at F. So what is F? F says, in another trial, the student dissolves a tablet of 55 milliliters of water instead of 50 milliliters of water. Predict whether the experiment determined the mass percent of I minus will be greater than, less than, or equal to. So imagine you put 50 milliliters of H2O, right? And you put it 1 tablet. But you can also put in 55 milliliters of water and the same tablet, okay? Would the percentage, mass percent of iodine that is in that tablet change? No, it won't change. So there's no change in iodine's mass percentage. Okay? All right, next one, G. Okay, G says A student in another lab also wants to determine the I- content of a potassium iodide tablet but does not have access to PbNO3 too. However, the student does have access to 0.2 molarities of AgNO3, which reacts with I- to produce AgI. The value of KSP for AgI is 8.5 times 10 to the negative 17. Will the substitution of AgNO3 for PbNO3 result in the precipitation of I- ion from solution? Justify your answer. So what we need to figure out is I have AgI versus, okay, I have PBI2, right? They are both going to create precipitates because remember, these are both part of the AP history, always insoluble solubility rule, right? So with that said, yes, it will make it. Also, the fact that this has a KSP value, okay, and it's like 8.5 times 10 to the negative 17, it's very, very small, okay? It's very small, okay? And even if you don't know, like if it's small or large or whatever, because relatively speaking, we don't know sometimes. So if you look at it, the fact that it has a KSP value, it tells you that it's insoluble, okay? At least for the sake of the AP exam, okay? So we say, yes, AgI will be produced. So we say, yes, AgI will be precipitated, okay? Because KSP value is very small, and also because silver paired up with anything other than nitrate is always going to be insoluble, okay? So this was the first question, and the second question for G, it says, the student only has access to one Ki tablet and a balance that can measure to the nearest 0.01 gram. Will the student be able to determine the mass of AgI produced to 3 significant figures? Here's the thing. So what happens is they just told you that, what is it? They just told you that the Ki tablet nearest, they're measuring it to the nearest 0.01 grams, right? And they want 3 sig figs, okay? This is what they want. So if you're looking at this number right here, how many sig figs does this have? It only has 1, right? It only has 1. So can you bring in 2 more significant figures based on this? No, you can't. And therefore, you say no, okay? It is only known to 2 significant, sorry, it has 2 significant figures, not 1, I'm sorry. So it's got no, will be known to 2 sig figs. Actually, no, you're right. So this is just one significant figure. It's 1 significant figure, but you can do plus or minus 1 and maybe have another one here. But besides that, you can't extend it to another 3rd figure. Okay, cool. Hope this makes sense. Thanks, guys. Bye.